Today I'm going to present some of the work that I've been doing using this targeted minimum loss based estimation. This is a bridge between computational data science and statistics. So there's a nice overlap for those data scientists as well as statisticians. So this is a nice way forward, I think, which has come out of the causal inference group, and targeted minimum loss based estimation was developed by the group in Berkeley, and it has become more and more prevalent in the last couple of years, last 10 years probably. And there is a R software for this. There's a superlearner package in R. And also, as you can see from my presentation, you can write yourself your own modules once you figure out the influence curve. So the TMLE is based. So this is a book that Mark Vanderlaan and Sherry Ross has written. So if anybody is interested, then you can have a look into that book. It's a nice book with a lot of examples, which lays a good foundation for both applications as well as theoretical. And like if you see the theory, it sometimes is very scary, but once you start looking at the applications, it gives you a good foundation of why and how to use this theory. Okay. So the TMLE is based on two basic concepts, which is influence curve and counterfactuals. I'll touch upon both of these aspects at length in the presentation, but just to start with, it is based on two concepts. One is counterfactuals and another one is influence curve. So I'll show you how to develop the influence curve later in the presentation. So the basic ideology, even though we are saying data scientist and data analyst, my motive is not to fit data to research tools or the tools that we have, but mostly to develop tools to answer a research question. So that is the motive. But because like once we say data scientists, we say that we want to fit different tools or different questions to the tools that we have. I don't want to do that, but basically to develop tools or to make use of tools to answer research questions. So when we say data and when we look at data, we have two different types of data sets, which is observational data coming from observational studies and also data from experiments. And these experiments are randomized control trials. The benefit of randomized control trials is it gives us a nice opportunity to have a balance of confounding, both measured as well as unmeasured. But there are some problems with experimental data, the randomized control trials. That is, when you have missing data, the properties of randomization are lost. And then it too acts as observational data, and we have to draw inference from using tools that are suitable for observational data. But then the question is, if every data is observational data, then how do we make causal inference using this observational data? There are several ways. One is to emulate a trial, that is by making use of the tools of, by making use of the tools of the trial design. We can set up the observational data as if it is a trial and then emulate it as a trial, and then to adjust or account for the confounding, observed confounding. We can use some of the methods that I'll discuss today, which is like inverse probability treatment weight and or marginal structural models or any of the G computation methods. And as a process, we can also deal with measurement error, missing data issues, and create and also look into those aspects. But what we cannot do is unmeasured confounding. Because we don't have any data regarding unmeasured confounding. So we have to do some kind of sensitivity analysis around unmeasured confounding, or make some assumptions around unmeasured confounding. I will also show certain assumptions which we need to make in the course of this presentation. But when we talk about observational data and use of observational data for causal estimation, the fundamental principle is to make use of counterfactual theory. I'll tell you why we need to make use of counterfactual theory in a moment. But this counterfactual theory has been used by Neyman in 1923 for randomized controlled trials. And Don Rubin, who developed tools for missing data, has actually developed the counterfactual theory for observational studies. And then Robbins in 1982 extended this counterfactual theory to longitudinal studies. And the theory that I usually use in my research is based on the methods that have been developed by Robbins. And why we need all of this is because when we are dealing with observational studies, we have both random error as well as systematic errors. And the systematic errors include information bias and unmeasured confounders, selection bias, and measurement error. And apart from that, we also have modeling errors, because we do not know the true distribution of the true parameter value of the data or the estimate. It is for this reason, whatever we assume the data generating mechanism or the model that it follows may be misspecified, and because of that we end up having model uncertainty. But what we tend to do in regular practice of statistical modeling is we tend to either ignore or just overlook most of these issues. But even though there are some methods for handling bias nowadays, which is done by Timothy Lash in the quantitative bias analysis books, but still it is not much prevalent, because either there is no software other than R packages, and if many people are not using R, they may not be familiar with these softwares. And it is for those reasons these issues are overlooked. But this whole concept of using counterfactuals, or even this need for the methods that have been developed under counterfactual theory, why do we need them? Is because in epidemiology, mostly people are interested in effect measure, but what we get from a statistical model without accounting for any of the selection bias or any aspects is we get a measure of association. If we just take a simple statistical model, and if we take a coefficient of that model, then what we get is a measure of association. But there is a slight difference between a measure of association and effect measure. Effect measure is a hypothetical concept, because it is the difference in the outcome when a person is given treatment and when the same person is not given treatment. We can't have that situation of putting a person in treatment and not in treatment at the same time. So that is the reason why I say effect measure is a hypothetical measure. But what we see often is people take this measure of association and interpret it as effect measure. But in epidemiology, we are interested in the effect measure. So how do we get that effect measure? It is for that reason, since we are putting the same person in two different situations at the same time, we kind of need a possible scenario development using the data that we have on hand. So that is what the counterfactual theory is actually doing, is creating that possible scenarios and then looking at the difference in the outcome under different scenarios for the same person. So that's how we get the effect measure. So now going back to Robin's theory of G computation, because these are some of the models that I'm using in my work. So here they have marginal structural models and IPTW weighting and structural nested mean models. So basically the IPTW and marginal structural models almost give you the same answer. There's no difference. This IPTW is less computationally intensive, whereas marginal structural models can be computationally taxing because you're duplicating data sets. But what is the difference between marginal structural model and the structural nested mean models is, let's say you have confounders at the baseline and you're interested in estimating the baseline exposure effect on your outcome. And if you have effect measure modification, that is if the effect of some of the confounder, if the effect of your exposure on your outcome differs within the levels of any of your confounders, so that is what we call effect measure modification. And if you have effect measure modification at the baseline, marginal structural models allow you to handle that. But in the longitudinal setup, if you have confounders and effect measure modification changing over the period of time, then marginal structural models do not allow you to handle that. And for that reason, the structural nested mean models have been developed to see if you have an effect measure modification over the period of time, and then how to handle that effect measure modification over the period of time. And not only that, the structural nested mean models also allow you to exactly estimate a specific time period effects. Like example, if you say there are 3 time periods of information that you have collected at T0, T1, and T2. So if you want to know what is the effect of T1 on your outcome, or if the effect at T0 is greater, you can actually measure those effects using the structural nested mean models, and you can actually say which time period matters most using the structural nested mean models. So the IPTW weighting is one concept that is of common to both this G computation as well as TMLE, because the base or the initial estimates for the TMLE makes use of this IPTW weighting, which I'll discuss in a moment. There's some notation, like if we have, let's say X is our exposure and Y is the outcome. And for this presentation, I'll be considering both X and Y to be binary. And all the code that I'll show for data generating is also based on this binary assumption. And the counterfactual theory allows you to get a marginal estimate as well as conditional estimates. So the marginal distribution of Y, you can write it like if you have X and Y, just X and Y. Then you can write the marginal distribution of Y as the expectation over X, and then the expectation of Y given X. So that's the conditional model. So that's how you can get the marginal estimates, by taking double expectation. So let's see what counterfactuals are and how these counterfactuals are created in the data set. So the first 3 columns are your data, which is observed. And when you look at the counterfactuals, how to create this counterfactual of Y when everybody in the population is treated. So how do we create that is we have the observed distribution of Y. So that's as it is. But these are the people. We are creating a what if scenario. What if all these untreated people are treated? Then how does their outcome look like? And how do we get this outcome? That's a predicted value. As you can see that I have written it as a hat of Y. So that's a predicted value. And in the second scenario, what if all this treated were untreated? How does their distribution look like? So this is the column that tells you about how their distribution look like. And again, this is a predicted value. And you get the distribution for this. But for these people, because it's already observed, so you have their own distribution, their observed values. So that means when we look at the marginal value, or when we are creating these counterfactuals, and when we are interested in estimating the marginal, we have two models here, as you can see, because this is the probability of x given c, so that is a model. And you have expected value of y given x and c, so that's again a model. So here you can see the importance of getting the models right to be able to predict these values and to get the counterfactual distributions so close so that the truth lies, we can get closer to the true value of the parameter of interest. Okay, so this is the reason why model uncertainty plays an important role in this counterfactual theory. So we need to be able to get estimates as close as to the true value, even if one of the model is incorrectly specified. So that's what the doubly robust estimation, or the procedures for doubly robust estimation, are more prevalent in this causal land, because we need to be able to get to the true value of the parameter of interest, even when one of the models is incorrectly specified. So to come up with, to be able to do that, there are two approaches. One is augmented inverse probability treatment weighting, and the other approach is targeted minimum loss-based estimation. So this is of more concern for today. So when we go back to the history, I always like to take some time to read where this thought process has evolved. And when I was looking at the history of this TMLE, I found the influence curve, I found that it dates back to 1974, when methods for robust estimation procedures have been developed. Of course, there are various other ways other than influence curve. We have M estimators, we have Z estimators, and you have S estimation. All this kind of robust estimation methods are there. But for TMLE, we are mostly using influence curve. And this was developed by Frank Hampel, a Swiss statistician from ETS Zurich in 1974. And this is mostly for infinite sample version. But before Frank developed this method of influence curve, Tukey jackknife estimator existed, and that is for the finite sample version. I can ask you a question. If you're a survey statistician, you must be familiar with jackknife estimation. And jackknife estimation is the closest to getting an influence curve. So let's see what exactly is this influence curve. You can see that influence curve is a derivative basically, but what this derivative gives you is a function, but not just a value, because usually when you look at this you get a tangent, and that would be your value. But here, in this example I'm showing here, is, let's say there exists a real line R, and in that you have some you have a function that is estimating the mean, like for example, and in the then you can define for all probability measures, you can see that for all probabilistic distribution there exists a first moment, and that first moment would be your mean value. So you have a mean for every probability distribution, let's say, and that is equal to mu. Then the influence curve, by using that definition, you can see there's this perturb parameter, that epsilon, and then you have the mean around that, because that is the value that differs for the differing probabilistic distributions. So you have that. And because we are estimating for any real value, you can get that value. You have that delta x defined for any real value x belonging to that real line. And now you can see you get a function here, which is x minus mu for every x belongs to R. Instead of getting a limit, a value, you're getting a function here. So that's why it is called as an influence curve of t on that probabilistic distribution. So basically you're getting a curve, and this curve now has some nice property. Because it's a curve, you can define supremum, you can define maximal slope, you can define points of height, and you can also see where this goes to 0. And also the variance estimation for this curve comes directly from the curve itself, which is called as the efficient influence function. And so you can get that. I'll show you how to derive all of these when I show the
Ali.
Sorry, Faisal, can you please mute your... Sorry, there is some disturbance. So now you can see some of these nice properties of the influence function. And the influence function, if you know the regularity of the behavior of this influence function, then you can together with some information on regularity, the influence function informs you about the detailed behavior of the estimator and how the separate observations contribute to the estimated value. Okay, so how each observed information contributes to the estimated value of the true parameter. You can also see that behavior. So now let's see, because in epidemiology, mostly we are interested in estimating the risk difference or the risk ratio or marginal odds ratios. So those might be the parameters of interest. Of course, there are various other parameters that can be interest, like attributable fraction and things like that, but I'm just giving you an example here. And let's say the first is the risk difference that is of interest, which is defined as the average treatment effect. And the average treatment effect is defined as the difference in the potential outcomes when everyone gets treatment and when everyone in the population doesn't have a treatment. Okay, so now the goal is to develop a double robust estimator that minimizes the impact of model misspecification. So that is the goal. And let's see how we can do that. To be able to do that, let's say we have some data and we have an understanding about some concept behind it, and we develop a DAG, which is a directed acyclic graph with some confounders, observed confounders, which are listed as C there, and your exposure is X, and then you have an outcome Y and unmeasured confounders. So now we need some assumptions, and those assumptions, the first assumption is the consistency. The consistency is nothing but how to travel between the observed world and the counterfactual world. So that is what the consistency assumption is. And also exchangeability, we need an assumption called exchangeability. What this exchangeability allows us to do is simply be able to predict the counterfactual outcome, because this is not observed, using the data that we have on hand. So it allows you to develop a conditional distribution like that, or conditional estimate, which you can do from your regression. And then we need something about positivity. The positivity is telling us that the predicted propensity score value lies between 0 and 1, and it is never equal to 0 or it is never equal to 1. I'll show why this is important later when we see the inverse probability treatment weight or creation of clever variables. And there is an assumption about the faithfulness. That faithfulness represents that the DAG is probabilistically a faithful representation of a system, in the sense a data generating mechanism. And so these are the assumptions about the DAG and relating the counterfactual world to your observed world. But when the interest is in estimating average treatment effect, we need to make one more assumption about unmeasured confounders. So this is an assumption about unmeasured confounders. What we are saying here is the counterfactual outcomes are independent of your treatment given your confounders. So they are conditionally independent. So basically all your confounders that you have observed have enough knowledge to tell about the relation between the counterfactual outcomes as well as the treatment. And then this allows us to now estimate the average treatment effect or marginal odds ratios. So now, how do we develop the doubly robust estimation under the TMLE, as I said, for the binary outcome? So first what we do is we predict, because it's a binary outcome. What I'm using is a logistic regression to predict my outcome in the first instance and label it as Q bar 0 XC. So that is the base right from your data. And then to predict the exposure, which is using a logistic regression, because my exposure is binary here, I've used a logistic regression. And then I get these parameters. I can estimate gamma naught and gamma 2. And these are bold because this is a vector, so you can have multiple confounders. It just doesn't have to be one confounder. You can have multiple confounders like H and so on, etc. So then once we have these two models, like once we have the model for your exposure, then you can create the probability of being exposed using your logistic model, and then the probability of being unexposed as 1 minus g hat 1c. So this gives you g hat 0c, and this gives you the g hat 1c. So then we need a clever covariate, which is called in this TMLE language. So what is that clever covariate? Is nothing but you divide the estimated probabilities from the observed exposure. If x equals 1, so that is 1 over the, so this is basically like a weight. And you can see if this goes to 0, this has an undefined value, and this goes to 1, like, because this is 1 minus. So if this goes to 1, then again you have undefined values. So that is the reason why we need that assumption of positivity here, so that none of these denominators go to 0. Okay, so we are creating these clever covariates, which are the inverse of these probabilities, as you can see. And once we have created the clever covariates, we need that fluctuation parameter, because in that limit, in the earlier slide that I showed, we have this epsilon, which is the fluctuation parameter. And this fluctuation parameter is created using the maximum likelihood approach. And how to create this fluctuation parameter is, because our outcome is binary, we are using a GLM, because you're regressing your outcome without the intercept using these clever covariates. And because this propensity will be close to 0, because this is a predicted value from your original outcome regression. And the difference between these two can be 0 if this is a perfect prediction. But if this is not a perfect prediction, then it can be little off. And because if this epsilon is 0, then we have a perfect prediction from the regular model, and we don't need any of these robust methods. But because we do not get a perfect prediction using the regular model, so we need this offsetting term, that epsilon. And now we can estimate this epsilon using this simple regression. And as you can see, none of these require any additional software because all of this estimation is done using your logistic regression. And here again, this is also done using a GLM, logistic regression. So that's the beauty of this approach. You don't need any additional software. But all you need to know is how to generate these concepts like clever covariates and also generate those weights. So once we get those fluctuation parameter, then you can update the initial estimate of your outcome to Q1 to create that as if everyone is treated, and now you can update the parameter using that computed or estimated fluctuation parameter using your weight from your exposure regression, and this is your initial value of your outcome. So this is how you can update the model from 1 to 0. This is in the instance where nobody is treated, and this is the instance where everybody is treated. Okay. So what you have to do basically is, in this model, you have to set x equals 1 once and x equal to 0. So you get two values. Okay. I'll show you when I start sharing the code with you. So you can see none of these require any additional software, as I said, but these are all straightforwardly computed using simple, regular standard software. And once you get the Q1 and Q10, which is the updated outcome, because these are the potential outcomes now, or the counterfactual outcomes. So now once you get the updated outcomes, you can find your ATE, which is the difference in these outcomes for each individual. So that's why this summation is running from I equals 1 to n and divide by the n so that you get the average treatment effect. And for the marginal odds ratio, you can just get these values and you can multiply with the 1 minus this value here in the top and 1 minus this value, because you're estimating an odds ratio. If you're estimating the relative risk, you don't need these two terms. You just need this. And then once we have estimated these parameters which are of interest to us, all we need is how to find the confidence interval. And the confidence interval you can estimate using the efficient influence curve. And what is that efficient influence curve? It's nothing but, this is the exposure, and you're weighting the outcome. This is the difference. This is the residual outcome, and this is the residual in your exposure rates, plus the difference if this is the true ATE. And so how do you get that? So these are all residuals. So you can see that efficient influence curve is coming from all the residuals. Okay. And again, this is the true, but we got to predict all of these values, which we have already. So we get all of this information from the predicted values. And because this is for each individual, we get the whole distribution. Now take the variance of that and divide by n, so we get the standard error. So again, this doesn't require any additional software, or you don't need to take samples like bootstrapping or anything, but because you can get straight away the efficient influence curve from your influence curve estimates. So this gives a straightforward way to estimate the standard errors. So now let me stop here and show you the code. So I need to bring up another. So here is the code to do all of this. I'll share this code on the website. So this is the logistic regression function. Can you see this? Can somebody tell me if you can see the screen? So here is the logistic regression. And then here is the data generating mechanism. I have generated C1, C2, C3, and C4. There are 4 confounding factors. And the first 2 are binomial distribution.
Some of the code is blocked out by a white square.
Sorry?
Some of the code is blocked by a white square.
Oh.
Yeah, it's wiped down. We can't see that C1, the code you're talking about. We're just seeing that at the end, the exponential x.
Oh, okay.
Yeah, that's better.
Yeah.
Oh, where is
Yep.
it? Where did that go? Sorry, can you see this
Yep.
code?
Yes. Yep.
Okay, so I can't see the code, but anyway, the code is the C1, C2, C3 are your confounders, and then we have the exposure, which is a binary variable, and the outcome, which is also a binary variable. But like you see how I have created the outcome variable. In the first instance, I have created the probability that's the y1, which is the outcome, and then the y0, which is again using the same values, but you can see how I created those probabilities. And then using that consistency formula, I have created y, which is the mixture of that y1, the exposure, and the 1 minus the y0 and the exposure. So that's how we can create the values. But maybe I'm just struggling to get that. I don't know where it disappeared. Anyway, so those are I just wanted to run it. I just wanted to show you. But if you scroll down, you can see there's observed data and how I'm running the GLM models in the first instance, which is following the steps that I showed in the PowerPoint presentation. So first instance, I have the model for outcome, and then I have the model for sorry. I'm just getting on. Okay. Anyway, but when I put up the code, you can see those values. You can go through the code line by line. You can see how I predicted all my Q0, C and X, and Q1, X and C, and Q0, X and C. And once I have that, so what I have done then is to make my estimates. and that you get the values like this using different models. All the code is given for each of the model, which is IPTW, augmented inverse probability treatment weight, and TMLE, as well as TMLE-R. I'm saying TMLE-R because I'm using the R software here. And there is another other option that you can use in R, which is using superlearner. The difference between this one and the manual one and the superlearner is slight. There's a very minimal difference. What the superlearner does is you have multiple libraries. Like you can use GAM, you can use random forest, you can specify a list of libraries, and you can make prediction of your outcome using each of those either parametric or semiparametric models. And then what it does is it gives you the predicted outcome under each of that model. And then now you can use those model as variable, and then because now the model is used as the outcome from each model is used as a variable, and then you can make a prediction of your observed outcomes against all of those predicted outcomes. So that's what the superlearner is doing. So that allows you to overcome the model uncertainty under the superlearner when you specify multiple libraries. So you can see the superlearner is giving you as close to the true estimate, even if the misspecified treatment or outcome models. You can see that the truth exists within those, within the data and within all of those models, because you're using that influence curve that allows you to estimate the true value of the parameter, either it be the ATE or your marginal odds ratio. So that's what you get. Whereas with the naive model, you're getting 3.1, which is your odds ratio, which is way off to what the truth would be. And then if you specify the treatment model correctly, then once again, the superlearner gives you the true estimate of the parameter. So now to conclude, the standard practices, because in the standard regular traditional regression based estimation, we just take the coefficient as the parameter value, but that is not really an effect measure, because as I said, when we say about or talk about effect measure, we want a person to be in two different situations, and the difference in the outcome when the same person is put in two different situations, that is what the effect measure is. And we do not get it as just a coefficient of a misspecified pattern.
بهت گفتم وقتی خودت عکس خودتو کلتو میبینی حالا وقتی خودت کلتو میبینی منم فقط کلتو میبینم. اگر اونو نگاه کن ببین کجاست. آره الان خوبه. آره یه گهگاهی به این عکس کوچولوی خودت که این گوشه هست نگاه بکن ببین صورتت کجا.
Sorry about that. Somebody turned the microphone on.
Oh, sorry.
So what then happens is different choices of misspecified models will give us different answers. And that's why we don't see any agreement. When we use different models on the same data set, we get different answers. We do not know the reasons why, but because of the different choices that we make of these models. And again, because with the targeted learning, we can see that it allows us to define the truth, and the truth exists within that curve that we are trying to that we can formulate using the data that we have on hand. And the benefit of this targeted learning is it allows us to resurrect again. As statisticians, we can be happy that this is a nice bridge between computational data science and statistics, and it actually bridges that gap that we think we are going to have with more and more data scientists and data science courses that are coming up. And also to lastly talk something about the big data. When you come to big data, and in these big data models, big data or linked administrative data sets, the TMLE would be more useful, because when we use the maximum likelihood estimation procedure that we are very familiar with, we know that it can lead to unstable estimates because of the curse of dimensionality of the model. And even when we regularize MLE, it is seriously flawed, because a general problem of the maximum likelihood is to care much about or approximate the true density, which will result in wrong trade-off of the parameter of interest. So these are some references which you can use to study more on these aspects that I touched upon. And thank you for listening. So if you have any questions, I'm happy to take questions. And you can all unmute, or you can raise your hand and I can see you. So
just put up the references again.
yeah. Yeah. So this is a paper by, it's a review paper, which is a nice review paper. And then here is the paper by Frank Hampel. And this is the structural models and causal inference in epidemiology. Again, this is a nice paper by Sherry Ross and Scheller in AJE, which gives you an overview of the targeted maximum, because even though it is now called as minimum loss based estimation, it was referred to as targeted maximum likelihood initially. So that's why you can see that name there.
Hi, Murthy. Can I ask you a question?
Yeah.
At the beginning of your presentation, you were talking about a nested, was it a marginal nested mean model?
No, structural nested mean models.
Ah, okay, structural nested mean model.
Yeah.
And it was very interesting what you were talking about there. That those kind of models allow you to pinpoint certain effects to a particular time point,
Yes.
which can be very difficult to do. And I was wondering whether there's anything, some pointers that you'd like to share for us to do some further learning.
Yeah, there's one of the reference by Robbins and Hernan that I have listed in the reference. That's a good one. There is another paper in the handbook of causal inference, a handbook of missing data. There's there's handbook of longitudinal designs or longitudinal data analysis. There's a paper by Hernan and Robbins using an example. And I also published a paper using dental data with the same one example. So if you want, just click me an email, I can share that paper with you. That's an example with the code. And also there is a very nice paper by Rhian Daniel in Statistics in Medicine, which is a tutorial which has a detailed example as well as data code, which you can use.
That'd be lovely. Thank you so much, Murthy. I enjoyed the presentation.
Thank you.
Thank you, Murthy. That was great.
Thank you. So I'm happy to take any questions that you have in regard to any of these aspects that you're interested in.
Murthy, it's Lyle Gurran from.
Hi, Lyle.
I assume you can hear me.
Yep.
So the so-called clever covariate,
Yeah.
which is so clever that if you read any of the introductory papers by Sherry Rose or Mark van der Laan or any of the tutorials, it's not explained how that's derived. It comes out of nowhere.
Yeah.
But my understanding.
Lyle, you're breaking.
This particular my question is, does the clever covariate change depending on what your target estimand is? I think yes, but that then means that you would need to get a handle on the efficient influence curve for those other targets, and that's not trivial. So what happens in the TMLE package and the R packages? And they clearly can't be deriving influence functions from scratch.
Yes.
So I assume, because I've not sort of used them at the nuts and bolts level, do they offer a range of things like the mean and the median or something like that as your sort of target quantity of the distribution? It's not clear to me how you generalize beyond simple
Boundary data.
Well, yes, not so much the type of data, but the simple summaries of a distribution. I mean, van der Laan has been spruiking this because the idea is that we can target any property of the distribution, not just the mean or the median. We target a quantile or the variance or some other, sort of supernatural function of it.
Yeah.
But that will require understanding of influence curves and things like that. So I guess my question is that those things have been solved for explicitly in this case and others, and are they the things that are coded up in the TMLE package?
Not very much, but because the TMLE is getting updated, they are trying to put more and more aspects into the TMLE package. But as you can see, the GitHub share that they have, they try to put, whenever they write a new function, they try to have that TMLE software for every new function that they are writing, especially when, let's say, if the exposure is a categorical variable, they have a new software and update. And if it is a continuous variable, I think in the superlearner, they have only for continuous exposure and binary exposure, and when the distributions are mostly mean and variance. But and because you're getting a curve, you can even approximate it for the quantile distribution. So those are the aspects that they have. But beyond that, if your parameters are mostly interested in skewness or something, then you got to write the special function.
Yeah. Okay. Thank you.
Yeah. No problem. Hi, is anyone having any questions or any interest? Or do you have some interesting examples that you think you would like to work on using this? I'm happy to learn or happy to discuss those things.
Hi, Murthy, it's Richard.
Hi, Richard.
Just a simple question.
Yeah.
I haven't used this much, so I'm sort of, a bit new to it all. Can you just confirm that the list of covariates that you're using is the same for both of the two models?
Yes.
Right. And second question, you very quickly showed in the results that there was a bias with misspecification of one model.
Yeah.
So if only the treatment model was correctly specified,
Yeah.
you'd get a very, very slight bias.
Yes.
Still.
Yes.
Okay, but you wouldn't get any bias in the misspecified treatment and outcome model. Oh, you do. Sorry, you do. You do.
Yeah.
Oh, you don't with the R package, but you did with yours.
Yeah. See, the doubly robust, like the TMLE works with, like in these examples that I have shown, they both are misspecified in both outcome as well as the treatment, the first one. Both models are misspecified. Like the treatment model is correctly specified in the second, but the outcome model is correctly specified. So the doubly robust concept works with misspecification in one of the model. Either it may be the exposure or the outcome, but not both. That's why the AIPTW is slightly higher. But whereas with the TMLE superlearner, because you are able to create multiple options. So with the manual one, I couldn't create many options, like creating interaction terms, creating nonlinear terms, and creating all those examples I couldn't do in the manual one, as you can see in the code. But when you look at the TMLE superlearner, because I'm specifying a library of functions which can have interaction, which can have nonlinear terms, which can have random forest, and all these kind of various libraries, I can define my influence function. And that's the reason why you can see the superlearner is very closer to the true value.
And you had continuous covariates.
No, in the simulation example, I have a couple of binary covariates as well as continuous covariates.
So that may be why the machine learning approach is, well, I mean, as you say, you couldn't specify a completely saturated model.
Yes.
With the machine learning, you get closer to that.
Yeah.
Okay. All right, thanks.
Hi. I think we can stop at this stage, but thank you all for attending and taking time to attend this presentation.
Thanks, Murthy.
Thank you.
We'll talk about it later, and
Sure.
thanks for the talk, and I'll follow up some of the references.
Yeah, thank you.
See you, Matt.